A radio transmitter can send music across a city. A satellite can deliver data across thousands of kilometers. But what exactly travels between the transmitter and receiver? The answer is energy. Electromagnetic waves are not just patterns of electric and magnetic fields, they are carriers of power moving through space. So far, we have learned that electromagnetic waves consist of electric fields and magnetic fields propagating together through space. We have studied how waves form, travel, reflect, refract, and interact with materials. However, an important question remains unanswered. Why do electromagnetic waves matter in communication systems? A receiver does not simply detect the presence of a wave. It must receive actual energy from the transmitter. Without energy transfer, antennas could not capture signals, circuits could not process information, and wireless communication would be impossible. This raises a fundamental question. How do electromagnetic waves transport energy through empty space? Understanding this mechanism is one of the most important goals of electromagnetic theory. Power in an electromagnetic wave refers to the rate at which electromagnetic energy is transported through space. The energy carried by the wave is stored within both the electric field and the magnetic field. As the wave propagates, these fields move together, continuously transporting energy from one location to another. The direction of power flow is perpendicular to both the electric field and the magnetic field. This means that energy travels in the same direction as wave propagation. The stronger the electric and magnetic fields, the greater the amount of power being transported by the wave. Intuitively, imagine water flowing through a river. The water carries energy as it moves downstream. Similarly, electromagnetic fields carry energy as they propagate through space. The fields themselves are the mechanism through which energy is transported. Physically, consider a transmitting antenna connected to an RF power amplifier. Electrical energy generated by the transmitter is converted into electromagnetic energy. The resulting wave travels outward through space and eventually reaches a receiving antenna, where the energy is converted back into electrical form. Mathematically, electromagnetic power flow is described by the Poynting vector. This quantity combines the electric field and magnetic field to determine both the magnitude and direction of energy transport. The Poynting vector provides a complete description of how electromagnetic energy moves through space. Power transfer is one of the central concerns in RF engineering. Every communication system is ultimately designed to move electromagnetic energy efficiently from a transmitter to a receiver. In wireless systems, transmitted power determines communication range and signal strength. Antenna gain, propagation loss, reflection, and absorption all influence how much of the transmitted energy eventually reaches the receiver. At the system level, power analysis is critical for cellular networks, Wi-Fi systems, satellite communications, radar systems, microwave links, and antenna design. Engineers constantly evaluate power budgets to ensure reliable communication under real-world conditions. Understanding electromagnetic power flow helps engineers answer practical questions. How much transmitter power is needed? How much energy reaches the receiver? How much is lost during propagation? These questions are fundamental to RF system design. A common misconception is that electromagnetic waves only carry information. In reality, information can only be transmitted because energy is also being transferred. Every received signal requires electromagnetic power arriving at the receiving antenna. As frequency increases, another important phenomenon begins to affect how electrical energy moves through conductors. Instead of flowing uniformly throughout a conductor, current starts concentrating near the surface. In the next lesson, we will explore the skin effect and discover why high-frequency currents behave differently from low-frequency currents. In this lesson, we learn that electromagnetic waves transport energy through space using their electric and magnetic fields. We also saw how power flow enables wireless communication, antenna operation, radar systems, and every RF link between a transmitter and receiver. In the next lesson, we will explore the skin effect and discover why high-frequency currents tend to flow near the surface of conductors instead of through their entire cross-section. If you found this useful, like the video, subscribe, and follow for the next lesson.